Okay, welcome everyone to the August 27th OMR Architecture Meeting. This is Mark leading today just because Daryl's on vacation, but we had a topic that wanted to be discussed, and if we have time and there's interest, I can give a brief update at the end on what's been happening with JIT-Builder 2 since the last time that I talked here. So I guess I will pass it over to Andrew, who suggested the topic to introduce it, and take it away, Andrew.
Okay, thank you very much, Mark, and thank you everyone for joining the call today. So I'm going to be introducing you to Jack Xia, who's a undergraduate student at the University of Alberta. He's been working with a group there headed by Professor Karim Ali, who's been doing research with IBM over the last I think it's almost 3 years now on a new novel inlining techniques and ways to do some great inlining in OMR and OpenJ9. And there's been a master's student, Eric Ochoa, who has presented and been present at these meetings previously, as well as a summary research student, Spencer Killian, who has contributed to this work. And essentially, Jack has been doing a lot of work cleaning up the code, tidying it up, re-architecting it, and is finally in a position where they would like to try and contribute this code to OMR. And I wanted to have Jack present to us all a little bit on what this is, what it looks like, what the contribution proposal is, so people can understand the sequence of pull requests that have been opened. So at this point, I'll yield to Jack, and he can provide you an overview of what's going on.
Okay, hello everyone. I'm Jack. So the BenefitInliner, so it consists of several different components. So the first one, and is one of the most important class, it is called IDT. So the IDT stands for inlining dependency tree. So it will hold all the candidate methods to be inlined. So the parent-child relationship in the IDT, it is corresponding to the caller and callee relationship. The building block of the IDT is called the IDT node. So the IDT node is an abstract representation of a method, and it contains useful information for inlining. For example, two most important information is the cost and the benefit. So the cost currently equal to the size of the method, and the benefit is calculated as the product of the method's call ratio. So it is actually the call frequency of a particular method and the benefits of the optimization from inlining this method. So they will be used for choosing methods to be inlined by the inliner packing algorithm. So
Jack, just before you continue, do you have any slides that you're presenting, or?
Actually, I think we can open the issue. So I think the issue has some.
Do you want to share your screen showing the issue so you can scroll through it as you're talking? Perhaps that might be easier.
If you control it, for sure.
Okay, sure.
So I'll stop sharing.
Okay, so can you see my screen?
Yes, we can see your screen now, Jack. Thanks.
Yeah. So in order to build the IDT, so we need an IDT builder. So IDT builder is used for constructing the IDT. So the two core functionality of the IDT builder is generating the control flow graph, and the other one is doing the abstract interpretation, because CFG is required when we do the abstract interpretation. So CFG generation and abstract interpretation, so they require language-specific implementation. So the OpenJ9 has one such implementation, and it will be contributed to the OpenJ9 project. So the main responsibility of abstract interpretation is to find the call sites and generating the inlining method summary. So this will be mentioned later. And the most important functionality is to simulate the program state. The inlining summary, so it will capture all the some potential optimization opportunities of inlining one particular method, and it will also specify what are the constraints that are the safe values to make those optimization happen. So the summary itself is not enough to determine which optimization will be unlocked after inlining. So we need the program state generated by the abstract interpretation. So we need to test the program state at against the method summary to see whether those constraints they are satisfied or not. Inlining summary is extensible and reusable. So currently there are some optimizations. For example, branch foldings, null check foldings, and the compiler engineer, they can extend those optimizations, and they can just compute their customized constraint through static analysis. And abstract value, abstract operand stack, abstract local variable array, and abstract state, so they are the very basic classes for doing the abstract interpretation. So the abstract value currently use the VP constraint as the constraint for different types of value. The next two classes is the BenefitInliner and the inlining proposal. So the BenefitInliner, so it contains the code for doing the inliner packing and the code for doing the inlining. So the inliner packing algorithm will analyze all the methods in the IDT based on their cost and benefit, and it will generate an inlining proposal containing the optimal set of methods to be inlined, and then those methods will be inlined by the inlining code. So
okay, Jack, if we can just pause before you go into the contribution plan, because I know some people on this call will have seen a lot of this inliner work previously and be fairly familiar with it, but there will also be a number of people on this call who have not seen it or have not seen it recently and probably need a little bit more of a high-level introduction to what this is and kind of what it's trying to do. So if it's okay with you, I'd just like to take a couple of minutes just to provide that overview so people have a better idea of kind of what all these parts are adding up to, since you did a good job describing the individual components, but I think people might need the higher level view, if that's okay.
Yeah, sure.
Okay. So traditionally, inlining has been done kind of with a single metric, right? So you have something like a size, and you provide a budget, because if you inline too much, right, it's not good. Your program gets too big. It's hard to analyze. It's hard to optimize. Algorithms in the compiler will blow up in terms of time or space. And so you don't want something too big. You also don't want something too small, because if it's too small, there's a lot of calls left in the code, and you don't have as much scope for your intra-procedural optimizations. So there's a balance point where there's kind of a sweet spot in terms of size. And so you want to try and pick the best possible things to inline when you're creating that given size, so that you have the maximum opportunity to improve the program's performance. Now, the inliner, so right now OMR has an inliner. It's called the trivial inliner, and it does not do any very sophisticated kind of inlining. What it does is basically, if you tell it to inline something, it will, and it's basically set up to just do very small, simple methods like getters and setters and that kind of thing. It doesn't do any sophisticated trying to figure out the right things to inline. Now, the main inliner that existed in the J9 project inside IBM before it was broken apart and open sourced as OMR and as OpenJ9. And the inliner, which is still in OpenJ9, is a very traditional kind of inliner in that it has a single metric size, and we try to pick things to fit within a given budget. And to incentivize the inliner to inline some things rather than others, there's loads of heuristics in that OpenJ9 inliner that increase or decrease the size of a method to make it more or less attractive. And this has a number of drawbacks, because if you have a very large method that looks very beneficial, you'll reduce its size. And you can have a very small method that may not look as beneficial, and you'll increase its size. And then you can't tell the difference between the two, right? Because they both have sort of arrived at this medium size. So one of the points in this research was to say, well, we want to separate the notion of how good inlining something is from how big it is, so that we can make better decisions about what we're going to choose to inline inside our budget. And there's this implementation that Jack has been working on has a solution to the knapsack with dependencies problem, knapsack packing with dependencies, where essentially you're saying, well, I can't sort of pick any random methods to inline because I need to have their call chain to the root method in there, right? Like I can't inline a method without inlining its caller, like the method that calls it, and so on, up to the method that we're compiling. So we have an implementation of that, and what it's trying to solve is, for a given budget, what is the maximum benefit? So budget can be kind of easily estimated as nodes or bytecodes or whatever you want. But the question is, what is the benefit? How good is it to inline a particular method? And the approach that's being taken with this work is to say, well, how good something is to inline is how much opportunity for optimization it exposes. So if I have a choice of inlining two things, it's better to inline the one that's going to let us optimize more, because it'll improve performance more. So the way that this has been modeled is using abstract interpretation. So there's an abstract interpreter with this inliner, which processes the program and calculates, maintains values for value ranges for operands, values, the intermediate program values. And it looks for patterns in the program that suggest an optimization is possible. So Jack alluded to branch folding. So if we see a test against null and it's branching one way or the other, we can look at the abstract constraint that's being produced for the value being tested and say, do we know that it's not null? If yes, we know that we're going to fold a branch. So we can say, we think that that's an optimization that's possible. Or you might say, well, actually that test is against a parameter. So we don't know until we look at the caller whether this branch will fold or not. And it records a summary of these possible transformations and the dependencies on parameters in that method summary that Jack was talking about. And so the idea here is to use this abstract interpretation to build up these benefit numbers, to have the benefit scores and the sizes, and then to pick an optimal inlining based on those numbers. And that's a very much more deterministic mechanism than many traditional inliners that are heuristic based. Now the implementation, most of this implementation is language agnostic, which is why Jack is looking to contribute it to OMR. The language specific component at the moment is the abstract interpreter, because a lot of this prototyping was done in the context of OpenJ9, and there, generating trees for all the bytecodes of all the methods you might want to inline is too expensive in terms of memory and time to be done. So you want to do your abstract interpretation over the bytecodes. So Jack does have a Java bytecode abstract interpreter, which he'll be looking to contribute to OpenJ9, I believe. But all of the common infrastructure, including the point where you call the abstract interpreter, and a lot of the infrastructure for building the abstract interpreter, is language agnostic and can live in OMR. And we also had a pull request open. I don't believe we've merged it, but there was a pull request that started an abstract interpreter for trees. And if we had that, then we could also abstract interpret trees and provide a basic inliner in OMR. And if a language wants something more efficient, like what OpenJ9 would, they can write their own for their own input format, so Java bytecode or whatever, to save having to generate trees. So the proposal is essentially to contribute, I believe, a performant inliner, a sophisticated inliner to OMR that is language agnostic, modulo this this abstract interpreter, and to let OMR provide that as a default capability to new languages, and to contribute to OpenJ9, OpenJ9 Java bytecode abstract interpreter for them to let them play with this inliner. So I think that's the high level view. And Jack, did you just want to speak a little bit about the sort of performance? You don't need to share specific results, but kind of what your experience has been running this code in the context of OpenJ9 where it's being prototyped.
Okay, so
Go ahead. Yeah.
I just wanted to know if there was any notion of frequency in this inliner that you described, because it didn't come up in the description, but maybe it's there somewhere.
Yes, frequency is there. It's included as part of the IDT and is used to scale benefit up and down to incentivize inlining of more frequently called sites.
Okay, thanks.
Okay, sorry, Andrew, could you just repeat your question?
So one of the things that the community will be interested in is how good is this inliner, right? It's being worked on for quite a while. Several people have contributed to it. I know you have been doing a lot of different performance tests with Da Capo, primarily in the context of OpenJ9. Could you just provide a brief summary? So how is the throughput? Is it sort of on par, better, worse than the current inliner in OpenJ9, which is being tweaked and tuned for the better part of about 20 years? How does it compare in terms of the amount of compile time it uses? And how does it compare in terms of the amount of memory that it consumes during compilation?
Okay, so the current benchmark test only captures 3 metrics. So the first one is the runtime, and the second one is the compilation time, and the third one is the generated code size. The memory is not being tested. So comparing with the OpenJ9 inliner, so the current OpenJ9 inliner, the runtime increase around 1% to 5% because the runtime may be affected by some other factors in the performance server. So it will increase around 1 to 5%. But the compilation times, it reduced around I think it's 18% to 20%, and the code size reduced also around 18 to 20% comparing with the current OpenJ9 inliner.
Right, so you're saying 18 to 20% less compile time and 18 to 20% less code. And on average, the throughput is roughly between 1 and 5% worse than the current OpenJ9 inliner.
Yeah, exactly.
Okay, great. Okay, thank you for that summary. So I think maybe we should pause if there are other questions that people want to ask. I know Jack has a detailed plan about how he would like to contribute this, and we can get into details, but I think it would be appropriate to give people opportunities to ask high-level questions here before we proceed further.
Just to make sure I understood those performance figures, so those are aggregate numbers across all of the methods that were compiled through the run of some program? Is that right?
Yeah, so the compile time and the memory, I believe, are across all of the methods, and the throughput was for the benchmark end to end.
However it measures. Yeah. Okay.
When you're running these benchmarks that you ran, was it mostly hot and scorching methods that were running? Because I mean, the default inliner that runs at warm is cheaper than what runs at higher opt levels. I just wanted to get a sense from those numbers what those numbers actually meant, whether it meant how much better the new inliner was versus hot and scorching primarily, because that's what took all the time, or did it say anything about the warm level inliner?
Did you want to answer that, Jack? Yeah, I understand the question. Did you want to answer that, Jack, or would you like me to comment?
I think maybe Andrew, you have more idea. So
okay,
about the actually the compilation level, yeah.
Okay, so for DeCapo, the throughput performance is dominated by hot and scorching methods. There is a non-trivial amount of warm compilation, but because the time is aggregate, I think that the dominant part of the compile time will be the high opt level compiles. There hasn't been a study done recently on something that's warm only. The code size, again, is probably dominated by the high opt level compiles just because they're the biggest ones. So is it a warm versus warm assessment? No, it's more high opt versus high opt.
Okay. Yeah, I just wanted to understand that better. Thanks.
Yeah, and I would say, just if I may add before your question, Mark, I would say that we would expect likely some increase in compile time and memory consumption potentially because the current inliner in OpenJ9 is greedy and will stop exploring the inlining search space once it's chosen enough things to inline that it's run out of budget. So it sort of conserves time by pruning the search space, whereas this inliner will search the whole search space to try and pick the optimal inlining plan. And for the sake of comparison, we're running them with equal budgets or roughly what as close to equal kind of budgets as we can. It may be possible because of the way the inliner behaves to tweak that to change the comparison at warm, but that work hasn't been done by the academics that have been involved in this so far.
Okay, I think that actually covered my question, which was going to be how you translated the greater budgets that a scorching or hot compile would have over a warm compile, how you translated that to how this inliner was going to operate.
Yeah, so they both have so in the embodiment in OpenJ9, they both use a number of bytecodes as their unit of size and their unit of budget. Now, it's not possible to do a complete apples to oranges comparison, apples to apples comparison, because the current inliner in OpenJ9 increases and reduces size based on perceived benefit. And so it's possible to fit more methods into the budget when you've artificially shrunk them, whereas the current one will keep the budget fixed but look for the best benefit that will fit. So it can lead to the current inliner inlining, like this proposed inliner, the BenefitInliner, inlining less, which is kind of reflected by the smaller code size and the lower compile time. But it seems to be holding its own in terms of the performance of the generated code.
Okay. Can you characterize, just like roughly quantify how much of this inliner is in OMR versus how much is needed in OpenJ9 to have a full implementation?
I would say that it would be something like 80 to 85% OMR, 15 to 20% OpenJ9. It's really the abstract interpreter only that's in OpenJ9. The rest is language agnostic and is being proposed for contribution to OMR.
Okay. And the OpenJ9 the abstract interpreter is bytecode based. Is that right?
Yes, the interpreter operates on Java bytecodes, but uses an infrastructure that is common. So you see point number 5 there is common, and it uses VP constraints, which are also common.
Yeah, I understand. Okay, cool.
Is the interface basically the summary is stored as a bunch of VP constraints and some other similar data structure, and that's basically what gets passed back from the abstract interpreter? Is that it?
Correct. So the language-specific part really is well-contained and relatively easy to sort of document and point at.
Right. So the rest of the algorithm kind of just works with those summaries and whatever other heuristics it has around the benefit, the perceived benefit that it derives from the summaries. All that is common.
Correct.
So some people here are familiar with the interpreter builder. I'm not sure what the state of interpreter builder is right now, but one thing that was missing from it was function lining. So I was wondering if this could be one solution to that, like IDT builder and this.
Yeah, I'll field that one. I'll field that one. So I don't think anything's been done with Interpreter Builder since the work that Robert, Charlie, and yourself were kind of involved in. There is actually a method inliner in JIT Builder right now, which Interpreter Builder is based upon. So there is an actual way you can call, if you call with a method builder as the target, it will inline that method's code right now. But I think the longer term story there would be more of a hookup into this inliner and having JIT Builder implement or provide an implementation of the abstract interpreter, possibly connected to walking JIT Builder IL, or it could also surface the abstract interpreter interface in some way up to the language to be able to do the abstract interpretation on bytecodes. But obviously none of that exists at this moment. That's just a notion in, I guess, my head.
No, good. Yeah, good to know. Thanks.
Does the abstract interpreter also have an understanding of frequencies in some way? Or does that only come in on the...
No.
Some other...
So the frequencies comes from the control flow graph. So we are currently generating the CFG using the estimated code size. So it will give us a fake CFG, but it is useful. So we use the CFG, the frequency of each block in the CFG for calculating the frequency of each method.
Yeah, whether you're going to include frequency as part of your benefit score for an optimization found within a procedure is kind of left down to the bit of code that sort of recognizes that opportunity. At the moment, I don't believe it's scaling using frequency. The frequencies are used to scale the call sites to adjust the perceived benefits as you traverse up and down the IDT.
Okay.
there is no reason you couldn't extend the benefit calculations to consider the intra-procedural frequencies, but I don't believe that's being considered at the moment.
Sure. Okay.
I'm interested in the delivery plan, which I guess is the next part of this. Is that right?
Yeah. So why don't we let Jack proceed with discussing the contribution plan and kind of what he has in mind for how this would get contributed, and then we can consider if there are more questions after that.
Okay, sure. So the contribution will be divided into 3 phases. So phase 1 is contributing the basic classes for doing the abstract interpretation. So they are abstract value, abstract state, abstract local variable array, and abstract operand stack. So after the phase 1 is being contributed, we'll move into the phase 2. So basically, it's the classes will be contributed are the IDT, IDT node, IDT builder, and the inlining method summary. So the phase 3 is the BenefitInliner and the inlining proposal. So yeah, that's it. That's the contribution plan.
Sorry, will it be included in any strategy at the OMR level as well? Op strategy list.
Because there isn't a language agnostic abstract interpreter at the moment, there is no way to include it in an ops strategy in OMR in a sensible way, because there's nothing to produce the benefits. So the project that I'd worked with at CanOSP on a tree interpreter was intended to try and provide the abstract interpreter you would need in OMR. The 2 students that were working on that had quite a bit of success, but only got an interpreter that was working on single basic blocks for a subset of the trees. I believe that PR is still open, and it would need enhancement before you could actually use this inliner in OMR in a language agnostic way. So the main way that it would be consumed at the moment is that because the researchers have created the abstract interpreter for Java bytecode, it can be that Java specific part can be contributed to OpenJ9 if that community is interested. I would imagine it would probably not be the default inliner for them to start with, but it would certainly be enableable under an option or something like that, I think would be the plan. It does make testing it in the context of OMR a little bit more challenging until that abstract interpreter for trees exists.
Yeah, that was a question I was going to ask about. So it looks like it's all kind of the implementation of the inliner itself, but if it can't be included in a strategy and maybe it's going to be hard to test it without an implementation of an abstract interpreter. I guess I was wondering if there is a plan, if there is some kind of notion for how this code could be tested while it's in OMR, or do we just have to get to the point of having that abstract interpreter there to be able to do something with it?
Well, I believe the IDT and the algorithm for picking the optimization plan can be tested in isolation. You don't even need to run that in the scope of the inliner. That can be just driven with examples, right, Jack?
Yeah.
So that part can be tested sort of standalone. I mean, the abstract interpreter infrastructure can probably have unit tests, but not anything more sophisticated than that. I think the part that would be the hardest to test is the stuff in phase 3, where you actually have the BenefitInliner, where you'd need some kind of abstract interpreter. but maybe we can mock one up that produces like some method summaries that don't have anything super interesting in them. Like we can just provide a benefit of 1 for a particular transform for each parameter or something for the purposes of testing. Just so that the code runs rather than doing something sensible with the full interpreter, pending somebody having the time to build the interpreter.
Right. So yeah, so I think that's an area that we'll want to spend a little bit of time thinking about how we can bring this code in and have it be tested in some way, shape, or form, just so that we can ensure as we go forward here that it doesn't get broken. And I would prefer that it not only get tested as part of OpenJ9, for example, which is kind of the obvious way it would get tested now, at least once it gets all contributed to OMR and then OpenJ9.
Yeah, I think that's a valid concern.
Do you have a time frame in mind for this contribution plan? Like, are you looking to start on phase 1 right away, or is it kind of a few weeks away? Or
Jack opened all the pull requests for all 3 phases already, and they are marked as dependent. So all the code is available.
All right, so I should just pay more attention. Okay.
I think that was just in the last couple of hours, wasn't it?
Yes, last couple of hours, yes.
There you go. I should pay more recent attention.
Yeah, so I've marked myself on those just because I'm interested in them, but we do need external review. I'm too close to these to do the review properly myself. And there's too much code here, I think, for one person. I think we need a few people to look at it. And I would especially like input from the likes of Philip and Leo and Ben and other people who have done a lot of work with testing in the context of OMR. I'm certainly not an expert on that, and I think that your expertise and penchant for good software engineering would be very appreciated in trying to come up with a way that we can get the testing going with the lowest overhead possible to Jack, since obviously he's got other things on his plate as well. But I would hate for all of this work to not be able to be contributed because of difficulties getting the right tests and things running.
Well, I mean, from my perspective, I mean, this is filling a fairly big gap in the OMR compiler infrastructure, and from the performance results that you've talked about, it sounds like it's filling it with something that's actually already reasonably effective. So I'm definitely in favor of seeing this in the code base, and I just want to say thank you to Jack and Andrew. I know you guys have spent a lot of time working on this, and others in the past on that project, building up this idea from nothing and getting to the point where it's actually a real thing that can run on real code, and getting it to the point of contribution. I think this is good.
Great, thanks, Mark. Are there other concerns that any of the committers would like to raise, just so that we're aware of them and can make sure that we address them as part of the process going forward? Well, I guess stunned silence implies tacit acceptance, so...
All right, let's merge it. No, I'm kidding.
Yeah. But my previous comment about the testing is very serious. I would really appreciate the people who are very into getting good testing going, jumping in and providing some insight and guidance on how we should proceed with that.
Fully agree on that one.
All right. So if there aren't any other comments here, I guess that's the end of that one.
Yeah, so I guess we're going to say that OMR is interested and willing to accept it, subject to some testing and review and all that usual stuff, and that we can take care of that in the PRs with comments from everybody looking at the code. All right, great. Thanks, everyone. Appreciate your time.
Okay, so I guess that didn't use up the full hour and a half. So the second item was for me to give kind of a verbal update on where I've been getting with JIT-Builder 2 since the last time I talked on this call. So I can't actually remember when the last time I talked about it was. So if I duplicate anything that I've already talked about, I apologize for that. But most of I haven't actually been able to spend a lot of time on it, so don't get your hopes up too much. But there are a few things that I've managed to incorporate into the JIT-Builder 2 compiler that, I guess I call it a compiler. It's about 7,000 lines of code right now, so it's a pretty small compiler, but it's based on top of the OMR compiler and JIT-Builder itself, so it leverages all of that infrastructure. Some of the things that I've added are I've added a function type as a fundamental piece of the JIT-Builder 2 intermediate language. And what that means is that when you call a function, you're actually calling a value that has a particular type that's a function type, which is essentially equivalent to a function prototype. And that type actually does get added into the type graph and verified as part of the operational requirements of making function calls. Unfortunately, I haven't done the code generation for function calls yet, so you can't actually generate a method of a function builder that calls anything yet, but you can generate the IL for it. You just can't generate code for it. I also have generalized some more of the infrastructure that makes up what an operation has. Anyone who's familiar with JIT-Builder knows that there are certain services that you call that you pass like an integer to, or a string, or a Boolean. I've kind of generalized all of those in the IL to be stored as literal values now, so that you can ask an operation about the literal values that it stores, and that enables some interesting, useful introspection capabilities. The main one of which is the thing that I've been focusing most of my effort on since the last time I talked to you guys, which is to build actually not a compiler, but a debugger. So the thing that I've been spending the most time on is something that allows you to debug JIT-Builder IL, so you can debug at the level of the JIT-Builder IL calls that you're making. So if you do a load, you can look at the result of the load. If you do a add, you can look at the operands of the add. You can look at the value that the add creates, and you can basically single step and do all kinds of things. So actually, let's see if we can make this work. I'm going to share a window. I'll do a little, I won't do a full thing here, but just so you can see what it looks like. I think it's this one. All right, does everyone see this list of all kinds of files inside my my little compiler here?
I see.
Yes, it's beautiful.
I'm flattered. It's flattered. All right, so what I'll do is, so I built this debugger thing, which if you pay really attention, it's right there, debugger. It's a very early implementation of this. I'm in the midst of revising it right now. But the basic idea is, rather than calling compile method builder, which would generate or compile function builder in this case, in JIT-Builder 2 case, to generate the native code. So it would compile all of the JIT-Builder calls that you make all the way down into native code, and it would hand you back an entry point that you could then run as a native function. The debugger works. You can call a different entry point, create debugger, I think I called it, something like that, and you pass it the function builder, and then what it does is it hands you back a native entry point that is essentially a thunk into a debugger that is tied to the intermediate language or the IL of the function builder. So what that means is that the interface to using the debugger is the same as the interface that you use to generating native code. So it allows you to basically just step into a function and debug it at the JIT builder level as if it was being called. Well, it actually is being called at runtime on the data. So you call this function as if it's a function entry point. It's as if it's the target function. So you pass it its arguments, and those get passed in as parameters that are then accessible inside the debugger so that you can see what's going to happen when you run that code. So one of the main reasons for doing this is because of the sort of many layers between someone who's writing JIT builder code and looking at native code, right, where you use the JIT builder API. Those are the function calls that you're familiar with making. Those in turn make calls down into the JIT builder layer, which then calls down into the OMR compiler layer, which builds OMR compiler IL, which doesn't look anything like the JIT builder calls that you made. And then that proceeds through, the obvious, compiler passes that the optimizer, performs on all of that code. And eventually it spits out native instructions. But it's a lot of steps through the code API that the developer is using and the actual output that you're getting. So it can be hard to sort of make sure that you're doing all the right things. So the idea was to provide a way for people to test just the IL that they're doing, so it would look like the code that they wrote. So what I'm going to do is, let's see, let's look at mult. We'll just look at this thing. So this is the standard matrix multiply JIT builder code. Hope everyone can see that. So this is just a refresher for people, right? So there's three for loops, the standard I, J, and K loop, and then the standard just run a sum through the A of I, K, and B of KJ, right? And collect them in a sum variable. So I don't expect you to absorb all this. Don't worry about it. I'll show you a different representation of this, but I just wanted to show, this is the kind of code that you write in JIT builder. So you're writing things like for loop up, you're doing load, you're creating const doubles, you're doing add and mul, things like that, right? So that's the kind of interface that you're used to. So I've actually already compiled this, so I'm not going to bother doing that. But I should show you the interface to it first. No, I didn't call it create debugger. What did I call it? So down here, somewhere down here, eventually here. So from method is just the function builder that gets built by that builds all of that code that I just showed you. You can ask for a debug entry with a prototype type. This is something I stole from borrowed from how the Trill compiler works, I think. And this will hand you back an entry point that you can then just call somewhere down here, right? You can just call test of, right, the output matrix, the two input matrices, and n, right? So you can just call it like it's a function. But what that actually does is pop you into the debugger. So I'll show you what that actually looks. So I'm going to just run it. All it's going to do is go through all of that code, and it's eventually going to call test on a function. Oh, I can't see that. There we go. So you can see once it gets down to invoking the compiled code, the JIT builder debugger, JBDB, pops up and wishes you a happy debugging session. It tells you which arguments got passed in for all the parameters and what their values are. So these are just addresses, and n is 4. So this is multiplying two 4x4 matrices to generate another 4x4 matrix. And it just automatically kind of stops at the beginning of the program. So it said that I could find a list of commands. So you can type in help and get this is the current supported list of things. It's loosely based on how GDB works. So if you use GDB, you'll be fairly familiar with these things. You can ask for help. You can get a list of the current IL, so you can get it to print out what the current method this should be function builder. Function builder's IL looks like you can single step through code. You can do next to jump over the full operation. You can continue to just let it run until the next breakpoint. You can print out values. You can print out types. You can print out symbols like names of local variables, and you can set breakpoints. You can list breakpoints. You can break before an operation or before a builder. You can break after an operation, and you can also break at a particular time. So part of the output that here is the time that has run. So time is just measured in number of operations. So we're sitting here right now before this load of A, right? So again, this is kind of very similar to what people expect to see. Why don't we just print out the whole JIT-builder IL that we've got here? So there's a little bit of a problem here in that the debugger itself creates a bunch of types and then it adds them into the type dictionary. So it prints out a bunch of stuff that you're not familiar with. So I'm not going to bother going through this, but basically the type dictionary summarizes all of the types that are being used by this function, and then it prints out the IL for the function itself, and it summarizes which type dictionary it's using, what code location is associated with this function, what its return type is, and T0 is just something that you can go up and look at in the type dictionary and see primitive, or it's no type, so this is a void function. That's not right. Oh, actually, it is right. And what the parameters are, what their types are, what local variables have been defined as this function was created, and then it goes and shows you what the operations are. So when you call this thing, it's going to go through a set of operations, and it just prints out, kind of like this. I think I've shown this in a previous meeting on what JIT-builder 2 IL looks like. And in this builder, it's just basically loading a bunch of parameters, and then it does the outer for loop and then returns, right? So that's kind of what the outermost builder object does. And then inside this for loop, you can see it's collecting the values together. So v4 is 0, v3 is n. So this is 0 to n by 1, basically, is this for loop. And it's a for loop up, and the body of the loop is b1. There are other for loop variants that give you a break builder and a continue builder, but this one only uses the body builder, RR. So B1, then you can go and look at what B1 builder does, and it basically just sets up the second nested loop, and then goes into B2. B2 just does again. It initializes the sum to 0. That should be printing out as a double, but didn't. And then creates the inner loop, and then after the innermost loop runs, it collects together the sum variable and stores it into the output matrix. And then finally B3 is the innermost loop, so it's doing all of the loading of the values and collecting the sum load sum, multiply the two things together, add it to the sum, and keep going. So that's kind of what the IL looks like. So then we can do kind of single step. We can go and print a bunch of things. So we are basically single stepping through the operations of the function, and then we can do we can see what the pointer of what C looks like. So C is a pointer to double, and that's the address of that in memory. We could PV v3, which would tell us what n value got loaded into v3, so that's 4. We could also print n itself and C4. So there's a bunch of things like that you can do. If we keep going here, eventually we get to the for loop. Now, if I hit next here, it's just going to do the whole for loop and get to the return. So that's not very interesting. So we can single step inside, and then we can start executing inside the for loops as they go. We can print v8, which is what the current sum is for this thing, as it's being initialized. And eventually we can just kind of go in and, we can see it's doing all kinds of things. So let's look at one of these PBs here. V13, we could say, is double 1. So double 1 is the value that it loaded out of the row 00 of the A array, basically. Right, and if you keep going, it goes and indexes into the B array and loads at that one too. So you can see that one is 0, so we're going to get a very unexciting value out of this particular row of the thing. Let me see if I've never actually tried to do this. So let's try breaking at something near the end. Let's try breaking at this operation here. 026. I don't think that worked, but anyway. All right. Did I get that wrong? Yeah, break before 026. There we go. So then we can do a compare, continue, and then it's executed up until that operation has run. So we can kind of take a look at what. So at this point, sum has the value 6 in it. And it does a bunch of other stuff and keeps going. So anyway, so that's just kind of interesting stuff. Eventually, it will. Too many of these things. Okay, I give up. It will eventually complete and run. I don't have anything to delete a breakpoint right now, so wasn't included in the list of commands, unfortunately. You can see all the breakpoints that you've got, but you can't delete one, unfortunately. So eventually this thing, there we go, will complete, and it basically returns and shows the execution of the thing. So the result of this matrix was produced by essentially debugging and interpreting the JIT Builder IL rather than actually building the intermediate language into native code and then running that. But it kind of replicated the whole same experience that you would get by doing a native compile. So that's my demo, which I kind of created on the fly, so I apologize if it wasn't very polished. The direction that I'm going in, so right now the debugger implementation is kind of a one-off that I did. So it's basically all the code it duplicates all of the code to simulate how to do an add and how to do a load and how to do a load add and index add and so on. So it's about 1,000 lines of code that if you were to add your own operation, you'd have to go in and add additional code to sort of support how that works. What I'm working on now is a way to do that without having to write so much code yourself when you add a new operation. So remember, one of the facilities or one of the things that I'm trying to build into JIT Builder 2 is the ability for people to create their own operations and create their own types with relatively little fanfare. And so if you have to go and implement a code generator for a new operation and then also implement an interpreter for it, that feels like a little bit wasted effort to me. So what I'm trying to do is create it's essentially going to compile a handler for each kind of operation and then insert some additional control flow, which it's going to use actually compiled function builders to do this, to essentially create all of the interpretation that's needed in order to be able to single step through that code and get the same result. So it will use the code generator that you implement for any new operation. So you only have to implement it once. And then by manipulating what code is in the builder objects that you pass to a new operation, you can actually automatically, I believe, generate the debugger that provides all of this support for using it. And that's pretty much it. I did also spend a little bit of time looking at creating a data flow engine for this, but I haven't made enough progress there to really report success. I mean, it's mostly mechanical things that need to get done. I just haven't gotten through it, and I kind of got focused on this debugger because it seemed kind of neat and cool. And that's kind of where it is right now. So let's see. I am still planning to contribute this JIT Builder 2 thing to OMR. I haven't really figured out the right way to incorporate it quite yet. So anyone who has suggestions, I could create a JIT Builder 2 directory in parallel with JIT Builder. I could create it as a subdirectory of JIT Builder, which is kind of what I have it in right now. I have it in a JBuild directory inside, or JIT Builder IL, inside the current JIT Builder directory of my private repo. But I guess my plan is to kind of clean up this debugger and get to the point of being able to contribute this into the project and hopefully get people's feedback and thoughts on it. And I'll stop there because I've been talking for a long time. See if anybody has any other questions or whatnot.
What are the mechanics of inserting the breakpoints in the generated code?
So that's really done in a very stupid way. Right now, at the beginning of an operation, it just checks a list to see if there's an active breakpoint that should cause it to break out into the debugger's user interface. So it's not done in any kind of smart way, but it's interpreting anyway. So I'm not sure it will get any smarter than that. Performance is not necessarily the topmost concern in my head right now. So, yeah. So I just did the dumb thing. All right. Well, if there are no other questions, then thanks for listening. And I guess that's the last topic that was on the agenda. Does anyone have any other topics that they wanted to discuss at the meeting today? Going once, twice. Okay. Well, thanks everyone for joining this episode of the OMR Architecture group. Once the recording is done, I will post it up so that everyone can see the replay, and I'll post a link in the project Slack in the general channel. Thanks everyone.
Mark. Thank you, everyone.